right, thank you, Professor Fujishima, for your kind introduction. And I appreciate all of the organizing committee members for giving me an opportunity to present our work here. And today, I'd like to talk about enzymatic reaction, enzyme catalysis, under using pressurized carbon dioxide. It's liquid or CO2 expanded liquid. My primary purpose of study is to develop green, sustainable organic chemistry. We need, for example, pharmaceutical is organic compound, and we have to synthesize it. And to synthesize it under a mild condition and an environmentally friendly way, I use enzyme. But I think study for the enzymatic reaction under high pressure carbon dioxide also help to understand the life science under extreme conditions. Because today I'd like to talk about the work study done by this student who just took a doctor, and also Christine Yamada-kun and Otsu-san. I think it's important to study enzyme activity under extreme environment on the pressure on the present and ancient Earth. Wherever life exists, enzymes are active, like high temperature, high pressure, high salt concentration, and high carbon dioxide concentration. As a catalyst, there are chemical catalysts and biocatalysts, and I use biocatalysis because of these advantages. It's natural, it works under ambient condition, it has high efficiency, and the carbon dioxide fixation reaction is one of the most difficult reactions to conduct using chemical catalysts, but enzyme can do it very easily. Energy selectivity is also excellent, so that's why I use enzyme for organic synthesis. And it's merit that aqueous media can be used as a solvent. However, there are also disadvantages of biocatalysts in aqueous media. For example, side reaction associated with water also occur. I will explain about this in the next slide. Extraction of the product from water, like pharmaceutical intermediate, have to be done using organic solvent. Hydrophobic substrates does not dissolve in water, and disposal of water is also problematic. Therefore, biocatalysis in non-aqueous media is important. And as a non-aqueous media, I chose carbon dioxide. Lipase is one of the most frequently used enzyme for organic synthesis because of the commercially availability, and it has broad substrate range, and it doesn't need cofactor, and it has high stability because lipase is already available in the immobilized form, so that it's even much stronger than the free form of the enzyme. And in nature, lipase hydrolyzes the ester and the aqueous solvent to acid and alcohol. But in organic solvents, it's catalyzed hydrolysis. So that because it's catalyst, if the forward reaction has lower transitional energy, then backward reaction also has lower energy. So this enzyme catalyzes both directions, and so that to make ester or polymer, well, there are a lot of polymer in nature, and polymerization reaction is also very important to understand the life science. And to make polymer, organic solvents or non-aqueous solvents are necessary, and CO2 carbon dioxide can be used. This summarizes the solvents used for the biocatalyst. Of course, water can be used. Organic solvent like for the case of lipase, 100% organic solvents can be also used. And recently, bio-based liquid from renewable feedstock is also important. Supercritical fluid can be used for the biocatalysis. Every substance can be under supercritical fluid, but for enzyme catalysis, of course, the temperature has to be around like 37 degrees, so that gas under ambient condition like carbon dioxide or chloroform can be used for the enzymatic reaction. Ionic liquid is also used. And when you think about the phase transfer, there are also solid layer of the immobilized enzyme. And you also can use additive hydrophobic polymer to decrease the substrate concentration and product concentration. It's sometimes necessary because there are substrate inhibition and product inhibition. Sometimes feedback from the enzyme are inhibited by the product. So these can be also used. And today, I mainly talk about liquid carbon dioxide and CO2 expanded liquid as a solvent for the enzymatic reaction. I will explain about the mixture reaction system and as well as two-layer reactions. All right, this tells you briefly about why I use carbon dioxide as a green solvent. Because it's sustainable, it's inexpensive, and it's abundant, recyclable, non-toxic. And also it's because the concentration in ancient Earth is higher than present day. And it's practically, it has practical merit. It's chemical inert so that it can be a solvent. It's non-flammable, low viscosity, and high diffusibility. This is very important for the rate-limiting, diffusion-limited reaction. It's non-polar, so it's dissolvable, the pharmaceutical intermediate. Product can be easily recovered without purification step, and it has high density of carbon dioxide. So it's favorable for a reaction using carbon dioxide as a reactant. And there are already industrial processes since 1970s. It's extraction of flavor, caffeine, and also dry cleaning use carbon dioxide. When I see the phase diagram of image of carbon dioxide, this shows phase diagram and image. This green is carbon dioxide, and this triangle is organic solvent. There are solid, liquid, and gas when you take temperature and pressure. There are also another stage called supercritical fluid, and the density change from gas to increase from this gas to supercritical fluid. The density of the carbon dioxide depends on the temperature and pressure. For the supercritical fluid, it has much higher density for the liquid, and when I use CO2 expanded liquid, it can be imaged like this. I mainly talk about liquid and CO2 expanded liquid as a solvent for the enzyme catalysis reaction. And this is the image. This is when you increase the pressure and the temperature, this liquid and gas state change to the supercritical state. Now it's supercritical fluid. So the enzymatic activity was first reported already in 1985, and then enantiomer selectivity or acceleration of the reaction have been reported. I started this study in 2000, but at that time, there were no practical organic synthesis in supercritical carbon dioxide. And then I did large-scale synthesis of chiral compound by lipase catalyzed reaction in supercritical carbon dioxide. But supercritical carbon dioxide needs high pressure and temperature. So recently, I'm studying liquid carbon dioxide and CO2 expanded liquid mixture of CO2 and liquid as a solvents. So this is the content of my study today. At first, I talk about lipase catalyzed reaction, and I found that substrate scope was expanded using carbon dioxide. I start with liquid CO2. So at first, I started with very easy substrate. So this is racemic compound. The lipase recognizes only R enantiomer, and R is acetylated, but S remains to be unreactive, so that we can separate them. We can make the chiral compound by using this reaction. And because this is an easy substrate for this lipase, when I examine the solvent for this reaction, liquid carbon dioxide and other hydrochloric solvent gave similar results. I tried other substrate also, and for this lipase, this one side of the substrate can be as large as phenol, but this small one have to be hydrogen, it's primary alcohol, or methyl, but when it gets to ethyl or larger, the reaction is difficult. And when I compare the result of hexane and liquid CO2, for the primary alcohol, it's about the same, but I see a big difference here using when one of the substituents gets ethyl. So for the easy substrate, the hexane and liquid CO2 gave about the same yield, but for difficult substrate, there were difference between hexane and liquid CO2. So I did more difficult substrate for the lipase. These parts are bulkier than ethyl. And then hexane and liquid carbon dioxide gave very different results. So for the difficult substrate, when solvents are investigated, liquid CO2 were much better than other. These analogous solvent does not have a significant effect, and pressure doesn't have significant effect. I pressurized the hexane to 7 megapascal, but this doesn't give the good results. The pressure necessary to change the conformation of the enzyme is 10 times more. The presentation is this morning, and the pressure used there was like 70 megapascal or higher, much higher, more than 10 times higher, or 100 times higher sometimes. So I don't think pressure gives any effect on the conformation of the enzyme. All right, so I wonder if the conformational change of the enzyme is reversible or not. And without pretreatment, as I said before, there are a big difference. So that I did the pretreatment enzyme. So that I put the enzyme under high pressure for a certain time, and then I put it to the normal pressure, and I did the reaction. Then the pretreated enzyme also doesn't give good result in hexane. That means the liquid CO2 induced a reversible conformation change of the enzyme. This is a proposed Carby structure of model in liquid CO2. There is a pocket here to recognize this part of the substrate. And in conventional solvent, because this is rigid, this part is rigid, so that big substrate doesn't get into the active side. However, in the liquid CO2, I think these amino acids get more flexible, so that bulky substrate also get into the enzyme. So far, reactivity and flexibility of the catalyst have been discussed under this symposium. So, of course, in high school students, textbook decrease in activation energy biocatalysts give higher rate of reaction. Change in the reaction pathway is also important, like breaking down a big hill to a small hills are important. And from the poster presentation of last night, I had increase of the substrate energy level by the solvent, so that if substrate here and transition energy is here, then increase of the substrate energy higher also accelerate the reaction, but increase in the enzyme flexibility is also important here, like so that enzyme level is higher, get higher by CO2, so that it's the transitional energy and relatively enzyme energy get higher, so that it's easier to get to the transition state. All right, next topic is carbon dioxide expanded bio-based liquid as a solvent. All right, when you pressurize a liquid with carbon dioxide pressure, the volume will expand like this. The pressure necessary is about 40 bar or 40 atmosphere for the case of THF, and it depends on the temperature too. And this resulting CO2 expanded liquid has better transport property because carbon dioxide has higher diffusibility. And solubility is improved when you compare with carbon dioxide, because there are organic solvent components. So when I compare organic solvent and carbon dioxide expanded liquid and liquid or supercritical carbon dioxide, viscosity and diffusibility is best for the supercritical carbon dioxide. But the solubility of the polar compound is better if the component organic solvent is polar. And the CO2 expanded liquid somehow has merit of both organic solvents and liquid or supercritical carbon dioxide, but it has lower pressure. For example, methyl THF can be made from the renewable feedstock. It's renewable, it's less toxic, it's biodegradable, and it has relatively low boiling point, so it's suitable for as a solvent. And if you pressurize it, the volume will expand significantly. And because depending on the pressure, you can tune the solvent property so that enzymatic property or enzymatic reaction can be tuned by pressure. Other solvents from biomass also can be bio-based would also expand. This is a case of methyl THF, but or other like limonene also expand. So this can be used further as a solvent. So I tried this very bulky substrate, and because this size is this is adamantium, so it's very bulky, so it's difficult substrate for the lipase. I also did the kinetic resolution to make the optically active compounds. And using the normal solvent like hexane or other bio-based liquid, the reaction didn't proceed. But if I add carbon dioxide, it proceeded smoothly. I tried with other kind of lipase, and some of them like this. PSA is better in using carbon dioxide, but not other lipase. Not always give good result. Other substrate also give better results when you use CO2 expanded liquid. Like these are very, very bulky, so that it's very difficult to synthesize, but it can be synthesized using lipase if carbon dioxide is used. Next, this one shows you how carbon dioxide, the activity is modulated by the CO2 mole fraction. This is the initial rate of the reaction, and using different temperature, and so it's normalized when it's plotted again to normalize to erase the effect of temperature. Mole fraction rarely affects activity. I plotted this graph again, changing the x-axis to the polarity. Then I again normalize. Then, well, it shows like this. And I think carbon dioxide concentration, molar fraction is more important than polarity of the solvent. This shows you another example of the modulating or controlling the activity using the pressure. In this reaction, enantiomer selectivity was controlled by the pressure. When the pressure is lower, in this case lower, it has a higher enantiomer selectivity. With other temperature, the highest and lowest was different, but because under different temperature, the density are different, so that, for example, at 31 degrees, the density changed very rapidly, and the enantiomer selectivity also changed very rapidly. So, yes. So, pressure can be used to modulate the enantiomer selectivity as well as the activity, substrate specificity. Well, this is not my study, but I just want to show this because I think it's interesting to see the surface of the enzyme. This is work by Professor Sylvier, and this is a molecular dynamic simulation result. So this is the enzyme I'm using, and this enzyme surface has were covered half by carbon dioxide and half by water. And because water blocks the carbon dioxide entry to the active site, so that the active site is the conformation of the active site is conserved, so that the reaction proceeds. And the substrate entrance is covered by the carbon dioxide, so that hydrophobic substrate dissolves into the carbon dioxide easier than to water, so that it can access to the enzyme easier, so that the reaction rate can be faster in the under supercritical conditions. Okay, so next topic is carboxylation in carbon dioxide water biphasic reaction system. So far, I talked about lipase catalyzed reaction, and the amount of the water is very small, and only essentially water on the surface or inside the enzyme are remaining. But for the case of this carboxylation reaction, enzyme is not strong enough and only under the carbon dioxide atmosphere, so that biphasic reaction were used. From 1970 to present, lipase has been widely used for the catalysis of the both forward and backward reaction. However, decarboxylase have been only used for the decarboxylation. And my goal is to use decarboxylase for the carbon dioxide fixation reaction. And in aqueous solvent, some enzymes were found to catalyze a reversible backward carbon dioxide reaction, fixation reaction. And with collaboration with Professor Nagasawa from Gifu University, I used this microorganism, the Bacillus megatherium, with the carboxylase. And I examined the effect of pressure. I conducted the reaction under atmospheric pressure and also under supercritical conditions, and yields were very different. Carbon dioxide fixation reaction in supercritical carbon dioxide is much more effective than under atmospheric reaction. And then I examined the pressure effect on this reaction, but when it's increased more, then yield decrease. Maybe because carbon dioxide dissolves into the cell, causing the decrease in the pH, or enzyme is not stable in high pressure carbon dioxide. Therefore, I need a stronger enzyme. Before finding the stronger enzyme, I just chose the commercially available enzyme for the carbon dioxide fixation reaction. And as expected, thermostability is low because it's mesoporous and it's from porcine heart or chicken. And CO2 stability was very low. Under two-layer reaction, system is quickly lose activity. So that I thought stronger enzymes are necessary, and I overexpressed the enzyme from this thermophilic enzyme, thermoplasma acidophilum. And then I checked the thermostability and the carbon dioxide stability. And as expected, high thermostability was observed, and also high CO2 stability were also observed. So high stability in high temperature may be related to the high stability in CO2. High thermostability and high organic tolerance were already published to be related, but I think carbon dioxide stability is also related because it's related to the rigidity of the enzyme. And then I did the carbon dioxide fixation reaction using the thermophilic enzyme. And well, in nature, isocitrate is oxidized first, and then after that, decarboxylation reaction proceeds. But I want the backward reaction, carbon dioxide fixation reaction. And but at first I tried without cofactor regeneration system. Then the reaction yield was low, even under high pressure. And then I overexpressed the glucose dehydrogenase from the same organism, and then I added the cofactor regeneration system. Then the reaction proceeded and yield increased. So, in conclusion, I examined the enzymatic reaction using high pressurized carbon dioxide. Is there still time? Oh, it's over? 4 more minutes? Okay, so first half is about lipase catalyzed reaction, and it's under 100% carbon dioxide or organic solvent. And second reaction, we're using 2-layer, but carbon dioxide still improve the enzymatic reaction. Okay, thank you very much for your attention.
Thank you so much for a very inspirational talk. Let's take questions from the floor.
Very, very interesting discussion, Matsuda Sensei. Question, in deep sea environments, liquid carbon dioxide sometimes comes from hydrothermal vents and separates, and because it is dense, it will form on the ocean floor as a layer of liquid CO2. Do you know if any life has evolved to use that environment? Maybe a more general astrobiology question.
I think there are microorganisms found in the carbon dioxide deposit. I'm not sure if it is deep sea or not, but in the 100% carbon dioxide deposit.
I mean, that sounds to me like an extreme environment, and yet you have shown elegantly that at least one major enzyme works. I'm wondering if other systems might have evolved to also use a pure hydrophobic liquid under those conditions.
Well, I think one of the group isolated the microorganism from the CO2 deposit, and they used in the supercritical carbon dioxide, and they did the expression of the enzyme, also enzymatic reaction. So I think there are organisms. Well, the reported organism also. I think it's not only the one organism living in the liquid CO2.
Thank you.
Any other questions? So I have a question. So the reason why the backward reaction works better so for example, even you're using the decarboxylase, which probably evolved to decarboxylate, the pocket still contains the shape which the CO2 can, and also the cofactors can bind. So the reason why the backward reaction can take place in the CO2 is purely because the stoichiometry-wise, you have dominant CO2, whereas in the aqueous, you have only the dissolved CO2. So the concentration of the CO2 level, is that the dominance? Or, like you said in the slide, maybe the solvent itself has a different, so maybe the molecule CO2 itself have a higher energy potential already, which driving the reaction. Which do you think is the dominant factor?
Well, in this case, there has to be a high concentration of CO2, but also when you concern about the energy, you need high energy cofactor, so that you need driving force. Okay. And for the case of the lipase catalyzed reaction, of course, because energy is not related, because if there are more water, there are more substrate, then water will react. And water is the substrate. So if there are more water than alcohol, then water will react. And without solvents, then depending on the amount of water, without solvent also backward reaction. It stops in the equilibrium position of these three components. But for the lipase, it's work and more under hydrophobic environment, because there is a lid cover on the enzyme, so the cover has to be open before it reacts. So and inside the cover is a hydrophobic residue, so it's better to it will open under hydrophobic environment. So that's why carbon dioxide is necessary. Or it can be hexane, but carbon dioxide do better. And I think maybe conformational change is caused by the diffusibility of the carbon dioxide. Carbon dioxide diffuse more, so that the lead structure and also other amino acids, particular amino acids, are more flexible. It's in the calculation under supercritical conditions. Some other researchers are checking the mobility, flexibility of some amino acid. For some amino acid, it's same under CO2 or solvent, but some other particular amino acids are different.
And I guess the flexibility in the supercritical CO2 is the opposite of what will happen in aqueous, because in aqueous, you have the hydrophobic interaction. But in the CO2 solvent, you basically start to see this flexibility at the position of these hydrophobic residues. So it's the other way around.
Yes.
Okay. Also, the time is up. So let's thank Professor Matsuda.
Thank you.